Good afternoon, everyone here. On behalf of my name is Dongcheng. On behalf of my group, I will make a presentation today. The presentation is a low-power single-cantilever gas sensor seal with remarkable recognition capability for food freshness-related gases. Okay, let me first give a brief introduction about metal oxide gas sensors. As well known, the sensing mechanism of metal oxide gas sensors involves two major functions, receptor and transducer. The semiconductor metal oxide acts as a receptor to gases, and the receptor function involves recognition of a gas in gas-solid interface, which includes electronic change in the surface of metal oxide. The conducts between metal oxide act as a transducer that transforms the gas reception into a change in device resistance. So typically, a completed metal oxide gas sensor can be divided into three parts. The sensitive material that interacts with target gases, the heat source that activates the sensitive material, and the detection electrodes that output the microscopic resistance of the sensor. So from the basic principle and the structure of the sensor, there are two main factors that influence the response. Types of the semiconductor metal oxide and operation temperature. So this work aims to make a kind of sensor that is of firstly high integration, because for more and more applications, especially those involving in recognition, we usually need to make multiple sensors or detection channels in one chip. And miniaturization is also the development trend of gas sensor. The second one is no power. Since the metal oxide sensor is a thermal device, when the number of sensors increases, power consumption needs to be taken into account as an important issue. The third is to improve the selectivity. As we know, the cross-sensitivity of metal oxide gas sensor is a long-term headache for researchers. So we want to improve the selectivity by combining temperature modulation and material modulation. The traditional structure of metal oxide gas sensor is to make the main parts of the sensor, including the micro heater, the detection electrodes, and the sensitive material on a closed or suspended membrane. In our previous works, we tried to make the sensor on beam structures, and we found that structures based on beams show potential in power, size, and integration. Meanwhile, by making full use of the heat transfer characteristics and the temperature distribution of the beam structures, it is expected to realize low power temperature modulation. In the past, we found that for single-cantilever micro heater, there is a natural temperature gradient from the fixed end to the free end, as the heat is conducted to the substrate through the fixed end. So if we make several sensing regions at different positions of the cantilever, the safe temperature modulation can be achieved. And if the sensitive materials in different sensing regions are different, then the material modulation can be achieved at the same time. So this work, we design a highly integrated 4-channel single-cantilever gas sensor seal, which combines self-temperature modulation and material modulation. Four detection channels with a common terminal share one heater. As usual, we did electrothermal simulation using constant multiphysics to verify and optimize the design. By adjusting the positions of the sensing regions, the temperature gradient between different detection channels is about 36 degrees, while the maximum temperature is about 400 Celsius degrees. And the deformation of the cantilever is about 15 micrometers. The manufacture of the sensor cell is absolutely based on typical semiconductor process. The low-stress supporting layer was fabricated by thermal oxidation and LPCVD. In traditional process, the sensitive layer is added after the whole macro hot platform was fabricated. However, in this work, we firstly patterned 4 kinds of metal oxides as the sensitive layers through 4 times of lithography and lift-off process. After that, we patterned the mental layer, including the heater and the detection electrodes at the same time. In the end, the cantilever structure was released through dry etching method. The characterization of the cantilever sensor cell and the sensitive material are shown in this page, including the top view of the cantilever, the detail of one sensing region, morphology, and EDS images of the sputtered materials. The left part of this page is a setup for a gas sensing experiment. The sensor cell was placed in a well-closed chamber, and the target gas was injected into the chamber to form an environment with specific gas concentration. After that, we open the chamber and allow the gas freely diffuse. The test circuit is based on resistor voltage deviation method, which is usually used in equation of metal oxide gas sensor signals. In this work, we choose 4 kinds of food freshness related gases as the target gases, as the gases injected in. The sensitive resistances of the sensor cell decrease, showing N-type characteristic. This page shows the radar charts of the sensitivity to the target gases. For different target gases, the shapes of the radar charts are so different, which means the responses to 4 target gases are channel dependent. We make a comparison about several works on single chip gas sensor array or gas sensor cell. This work is potential in low power gas recognition that involves both temperature modulation and material modulation. In summary, in this work, we design a low power 4-channel single cantilever gas sensor cell with different patterned sensitive material. By taking use of the natural temperature gradient of the single cantilever, the sensor cell has both working temperature modulation and material modulation to improve the selectivity. The sensor cell was fabricated by controllable and reliable semiconductor process, including the fabrication of sensitive materials. And the sensor cell shows recognition capability for food freshness related gases. That's all. Thank you.